Alrighty, we're going to talk about how to increase the rate of reaction, how to make a reaction go faster. Because if you're a mad scientist, you can't wait around all day for your reaction to go on. And we're going to focus on 3 ways to do this. We're going to talk about how to change temperature, what catalyst is, and what happens when you change the concentration. So to talk about temperature, we're going to think about popcorn. And so as we see, we make popcorn. Obviously, one burner is hotter than the other burner. And as we watch this, besides the fact that one burner is red and one burner is not, we see that one pan, we start seeing popcorn pop, and one pan we don't. And up there goes, that's like the peak, that's like the activation energy. All of these popcorn kernels now have the energy to pop, to become popcorn. And so with this higher temperature, the kernels react and turn into popcorn faster. So high temperature makes the popcorn pop faster. And so that means that the higher temperature brings more kernels to activation energy. That brings more kernels to the temperature that they need to be popped faster than the low temperature was. So now, let's look at this graph. So we know the shaded area represents the number of molecules that have their activation energy, the number of molecules that have enough energy to become popcorn. So which one would represent the higher temperature? Well, this line right here that has more area, if we look at the blue lines, we have more area of blue lines than we do red lines. So this more area shows that there's more molecules that have the energy to pop or to react or become whatever it is they're trying to become versus in the low temperature. Our bonus, what is EA? EA is our activation energy. So now we're going to zoom out of this graph. The blue line is actually the shorter hump. So even though this line is taller, if we say that this area under the curve is how many molecules have activation energy, then it makes more sense to say that T2 has more area under the curve, more molecule with enough energy to react, so T2 has to be the higher temperature. Bottom line, the height of the curve tells you nothing. You have to look at the area under the curve. And your particles have to have enough energy, that activation energy, when they collide to make a reaction. So try and figure these two out, pause the video, figure out which is the greater temperature, T1 or T2. So we see that in both graphs, T2 has a greater area on the other side of this EA, this activation energy. So more molecules have activation energy, have enough energy to react with T2, meaning that T2 is the greater temperature. Because at high temperature, we have more molecules with more energy because that temperature, that heat energy is going into the molecules. So at higher temperature, we have more molecules with enough energy to react. So now try to rank these. Based on what we've talked about, this one up here will be the 0, because if we look, that has a little tiny bit of molecules that can react. This one should be the 25 because that has the medium amount of molecules that can react. And this bottom one is our 100 degrees Celsius because if we look, that has the most area under the curve compared to all of the others. If we include all of these other areas, it has the most. So now we're going to look at another demo. This says yeast and peroxide. So that's yeast that I'm dumping into that cup. And we see the one with the yeast form bubbles, and the one without the yeast does not. So let's talk about what's going on here. We have a catalyst in yeast, something that speeds up the reaction by lowering the activation energy. So the catalyst makes it so that the molecules don't need as much energy to react. So you can have reactions at a lower temperature. The products don't change, only the time of completion. So you're going to get the same thing, it's just going to get you there faster. So hydrogen peroxide, normally it doesn't bubble that much unless you put it on something that it's going to react with. If we add a catalyst like yeast, or like when you put peroxide on a wound, it starts to bubble. And so the peroxide bubbles over time, but when you add the catalyst, you see lots of foaming bubbles. Our meme, the activation energy is too damn high. So we add a catalyst. So why does peroxide bubble on a cut, and why did the peroxide bubble with the yeast? Because in our cells, and in the yeast cells, we have an organelle called peroxisome. And so as a GIF right here, when we add blood with peroxide, we see foam, just like we did with the yeast. And that's because in the peroxisome, there's an enzyme, proteins that speed up a reaction, in case you forgot from biology, called catalase. And these enzymes, remember, they speed up the action. The catalase works specifically with peroxide, because if peroxide gets into our body, it can start to cause damage. So our cells take up the peroxide, send it to the peroxisome, and this breaks it down faster than if it was just traveling in the body by itself. We can think of it as like a puzzle piece, and so the reactant goes into the enzyme, into the catalase fits it perfectly, and then breaks it apart and spits it back out. The same thing happens in the yeast. That's why we see those bubbles. This oxygen gas is what is produced in the bubbles. And our meme, baby, you must be my catalyst, because you increase the rate of my heart. So if the catalyst lowers the activation energy, then which line on this graph, we've seen these graphs, if you forgot, go see the reaction coordinate diagram video, which of these lines represents the catalyst line? So we said it lowers the activation, and from reactant to peak is activation. So the lower one, this one right here, this is our reaction with the catalyst. So we see we don't need as much energy to get started. Same thing over here. At the peak, that's where activation energy is. The catalyst lowers activation energy. So from reactant to peak, we don't need as much energy. This line right here is the catalyst line. So here's our activation with no catalyst. Activation with the catalyst. It's much smaller because you don't need as much energy. Same story over here. Activation without the catalyst, activation energy with the catalyst. And our meme, was a cat need to do shopping quickly? A catalyst. And so let's think about it on this graph. So on this graph, this line right here, this vertical line, is our activation energy. The y-axis increases as we go to the right. So that means it decreases as we go to the left. So if this is the original activation energy, if we add a catalyst, that line gets pushed back. So instead of this little tiny bit of molecules that has enough energy to react, we have this larger area of molecules that have enough energy to react. Same story on this side. You can pause the video and read these later if you want. Here we have the number of particles without catalyst, the number of particles with catalyst. So we're going to talk about the last factor, concentration. So I have cornstarch. I put a little bit in 1 cup. And I add about a 1/4 cup of water. And that's to make a solution of the cornstarch. So then I take a little bit of that solution and then I dilute it down with some more water. Then I take a little bit of the diluted solution and make that one even more diluted. And so when you dilute a solution, you have more water molecules than you do whatever it is you're diluting. So in this case, the number 1 has the most cornstarch molecules, while number 3 would have the least. It has more water molecules. Now I'm adding iodine because iodine reacts with cornstarch. When iodine reacts with a starch found in corn or potatoes or rice or bread, it turns purple or black. So as we can see in number 1, it's the darkest, and so we have the strongest reaction there because we have more molecules able to interact with that iodine. We have more molecules that can cause this reaction, so we see a stronger reaction. So when you increase the concentration, you're usually going to get a faster reaction. That's why you can use a concentrated peroxide to bleach your hair. It doesn't work as well if you use the one that you put on a wound. And so if we look at this, the low concentration has a couple of molecules, and the high concentration has a lot of molecules. So the high concentration, you increase your probability of having a collision, and you increase your probability of having an effective collision in the right orientation because you have more molecules bumping into each other. So high concentration means more particles, means more collision, means more reaction. And our meme, a 1 molar concentration, because this is a molar in a solution, so it's 1 molar. So let's think about this one. Which one's going to react more quickly? This one with more molecules will have more collision, so it's going to react faster. It's going to have a faster rate of reaction. This more concentrated solution falls to the bottom faster, or makes the whole cup yellow faster than the one with a lower concentration of yellow dye. And that is it for today.